see that sometimes we have acids and bases that are kind of hidden from us, or that we get a solution with a non-neutral pH when we dissolve a salt in it. For something, of course, like sodium chloride, when we dissolve that in water, we expect it to be neutral. But why? Why would that be neutral but not others? The reason lies with the idea of the conjugates. If we take the idea of sodium chloride, we look at what it's made of, right? Na plus Cl minus. We need to recall that the conjugates of these, the conjugate acid or base, would be the following, right? We know that NaOH, because Na is positive, we can't put any hydrogens on it, doesn't make any sense. HCl or Cl is negative, so we're going to want to put that with hydrogen, H plus. We see that these are both strong. We have a strong acid and a strong base. And so as a result, we have negligible conjugates. So both sodium and chloride are negligible in terms of their acidity and basicity. So they will not contribute to the pH, changing the pH within a solution of NaCl. However, if we take something like sodium fluoride, for example, we know that sodium comes from NaOH, sodium the positive one, again, usually is from the base, the negative one from the acid. If we write out those formulas, we know that we had sodium chloride is strong, sodium hydroxide is strong rather, but sodium fluoride is weak, which means that the F minus is a weak base. And the sodium, of course, is a negligible acid. So sodium's not going to figure into our pH of our solution, but the fluoride will. The fluoride is actually a weak base. So when we dissolve sodium fluoride, which looks like sodium chloride, just white granular solid, when we dissolve that in water, we get a weakly basic solution, meaning it's slightly alkaline. It's got a relatively high pH. It's not neutral, but it's actually got a relatively high pH. And if we were so inclined, we could calculate that pH, right? If we had 0.1 molar NaF, remember we can kind of ignore the sodium here because it has negligible acidity. So really what we're looking at, again, this is a soluble ionic compound, so we're looking at really 0.1 molarity of the fluoride ion. And then if we were really going to calculate the pH, we would then find the Kb of fluoride, and then we would go from there. We would go ahead and do our calculation with the ICE table. We would go ahead and solve for X, calculate the POH, I suppose, first, and then we would get the H plus, or the pH after that. So we would use the Kb to do an ICE table to find the OH concentration, which then we would find the POH, and then we would find the pH from that. So all of that you should be able to do. That's from our previous videos. So really here, we're in this section, we're just identifying kind of the aspects of salts that could be used to then do these Kbs or Kas as necessary. Well, we can, by the way, see this with acids. For example, ammonium chloride. We know that this is ammonium and chloride. We know that this conjugate would be ammonia, and this conjugate is HCl. We know that HCl is strong, so we don't care about the chloride. Chloride's a very weak base, negligibly so. This is a weak base, which means that ammonium is a weak acid. So we need to use the Ka of NH4 plus to find the H plus to find the pH. So if we were to do that. So we would need to do an ICE table and all that fun stuff to find our concentration of H plus. Apparently we have a software update as well, and then we can find the pH. So with this, kind of got to think about your salts. What are they made of? Do they have conjugates that are weak or strong? If they have strong conjugates, then they themselves are negligible. We can forget about them. However, if their conjugates are weak, then they are also weak. So ammonium is a weak acid, and so it will lower the pH of our solution. And so we were going to need to use the Ka of ammonium, which we could solve for the Kb of ammonia, by the way, don't forget about that, which then we could use to solve the pH of the solution. Sometimes, by the way, there are some interesting things that happen in complex ion chemistry. For example, when we think about the iron 3 ion, looks normal, it actually is quite acidic. We're going to see that many +3 ions are actually acidic for the most part. And those are iron, chromium. I have to cheat here and look. We've got our 3+1s. These are fairly acidic. And then we have some +2 ions. So iron, zinc, and nickel. These are kind of weakly acidic. Like, they're really not very acidic at all. Their Kas are quite low. For example, for this reaction here, this is using a notation we're not familiar with yet. But what happens here is we have an iron 3 ion surrounded by waters. It's hydrated. We need 6 of those waters. When another water comes along, the iron being so positive is going to start dragging electron density away from the oxygens, which makes those H bonds even weaker. And so we can actually remove them. And in doing so, you have an equilibrium. You do not need to memorize this example at all, by the way. But we end up producing an acid in solution. We'll end up losing one of our protons off one of the waters that's on the iron, forming a hydroxide, which will help stabilize the iron, and we also produce that H3O+. And therefore, this is acidic. And actually, the Ka for this is 6.3 times 10 to the negative third power. That's actually pretty high, relatively speaking. Higher than acetic acid, right? Acetic acid is 1.8 times 10 to the negative 4, so, or 5, somewhere around there. This is much more acidic than that. So you can also have metals that contribute. And so in Discord, as always, you'll have a list of Kas of some metal ions, so you can work with those as well. So even if you put FeCl3 in solution, this will actually be pretty acidic because of that iron 3 ion. The chlorines, again, don't matter, but the iron does. So really what it comes down to is you've got a couple things to look at. You really have 4 options, actually, overall, when you're deciding if a solution is acidic or basic. Again, you could calculate the pH, but if I just ask you, is this solution acidic or basic? We can kind of come up with 4 categories. We have what could be a neutral solution. For this to be the case, both ions are negligible. For example, NaCl, or KBr, or why not, how about lithium perchlorate, whatever. Something like this. All these ions are negligible in terms of their acidity or basicity because their conjugates are strong for both. So your solution should be neutral. Option 2 is you'll have an acidic solution. Acidic solutions are going to be when your cation is weakly acidic and the anion is negligible. For example, iron 3 nitrate. The iron 3 ion is acidic, but the nitrate ion is not basic. So you have a weakly acidic cation and a negligible anion. Another example would be something like, why don't we have ammonium bromide, right? Bromide, negligible anion, which is therefore a negligible base. We have a weak acid as part of our cation. So we'll end up with an acidic solution. Option 3 is we'll have a basic solution. In this case, it's the opposite. The cation is negligible, and the anion is weakly based. Let's try this again. Weakly basic. There we go. For example, sodium acetate. Or how about potassium oxalate? Your cation is negligible. Your anion is weakly basic. So again, you look at the conjugates. Conjugate of K plus would be KOH. The conjugate of C2O42 minus is H2C2O4, or technically, if we're looking at the real conjugate, it's one hydrogen, but in either case, that's still a weak base. So we're looking at these. That's a basic solution. All right. The last category is the tough one. We have weakly acidic cation, weakly basic anion, and what the heck does that mean? In this case, we have to look at the strengths of them. We need to see which one is stronger, which one has, you're comparing the Ka and Kb. Compare the Ka of this one and the Kb of your base. Whichever one of these is higher will determine what your solution will be. If Ka for your acid is bigger than Kb for your base, then you have an acidic solution. If the Kb is bigger than Ka, then you have a basic solution. So for example, if you have Fe, what's a really, really weak base here? How about sulfate. Something like this. When you look at the pK of this, it was something around 10 to the negative 3. I don't remember the real number. For sulfate, you'd have to look up in your Ka table. You'll see that the Ka for this thing, about 10 to the minus 1. So therefore, Kb for the conjugate, is somewhere around 10 to the negative 13. Right? Because remember, they have to add up to 14. So if we look at this, we see, this one is bigger, therefore this solution will be acidic. So that's what we're looking at here. When you have two, when both of them are weak, you just have to compare. This is the Ka of iron 3. This is the Kb of sulfate. Kb1, actually, it's the first base reaction. But that's what we're looking at here. So in this case, the iron is clearly going to win out, so our solution will be acidic overall. If they happen to equal each other somehow, like ammonium acetate, it would be a perfectly neutral solution because Ka and Kb are equal to each other. So that's a very rare circumstance, but that would be neutral. So whichever one wins, that's the end of the day. So that's how salt solutions work. So you can even do pH stuff on things that don't even seem like acids or bases.